So my presentation and my results of studies, a scientific approach and not concern the technical details of Brewer, and it shows a possibility to apply and use the aerosol optical depth data from Brewer for scientific problems. The co-author Zoltan, my colleague, and these studies and the results of my results and calculations, but his background work is very important, so that is the reason that he's a co-author. We have a relatively good background and history of several optical depth studies, about 20 years, and the UV Aerosol Optical Depth study is very brand new. It's very brand new because I started some weeks before this meeting. We use the Brewer software that calculate aerosol optical depth from 2010, but I had no enough time to deal with the data. So practically, it was my official plan in my institute to started to evaluate the data sometime this year, but this meeting was organized to March, so I decided to try to make some preliminary results to this evening, to this meeting. So first, it was only some seconds. I will show some details of our solar radiation station that is completely measures several components of solar radiation. And secondly, I will show you our scientific background or results that we found in the past for several aerosol optical depth studies. And the third part, I will show you our preliminary results of using UV optical depth coming from Brewer measurements, and show how they can be inserted into the aerosol optical depth study background that we found in the past. We measure several solar radiation components in 1 minute temporal resolution. You see it is on the list. I don't want to explain something I think most of you knows, that parameters. It is a basic components in a complete measurement program, solar radiation station. So I started to study optical depth in the early 90s when we have no spectrophotometer, any spectrophotometer, only traditional classical broadband solar radiation devices, but it seems to be useful to know transparency and the long-term transparency, long-term change in transparency of the atmosphere above or observatory in Budapest. So I started to use some parameter to describing the transparency conditions of the atmosphere. First is the scattering parameter, and second is the gray body optical depth that I will show you briefly how I retrieve it. And later, when we purchase and install or spectrophotometer in 1995, I started to use aerosol optical depth for the 9, or if you want 10 standard optical depths that is correctly calculated in the visible range and in the near ultraviolet, and calculate wavelength exponent, angstrom exponent for every spectra. So it is the scattering parameters. It was relatively commonly used in the past in solar radiation stations. It very briefly, the definition is this of this parameter is that it is a ratio of diffuse to global ratio of the measured diffuse to global ratio to to the same ratio, but calculated for the Rayleigh atmosphere. And it can describe the transparency of the atmosphere relatively well. I don't want to explain anything. And great band optical depth, it is a bit my creation, but very useful if you have correct per-heliometer measurements for the direct radiation. It is an extension of the definition of the monochromatic optical depth, and mathematically a bit inverse of the Planck or Chandrasekhar or Rosselland opacity that is used in the line-by-line radiation transfer methods. I imagine the definition, so it is absolutely the same like the monochromatic optical depth, but the definition extended to the sensitivity range of the per-heliometer. So it is a very averaged and general parameter for a general, not real average optical depth for that very wide range. Aerosol optical depth is, you know well, I think, so I don't explain anything. We started to calculate and use aerosol optical depth from our LICOR spectrophotometer. It is basically it is a spectrophotometer. It means the spectral global radiation, but we designed and built a special pipe to it, and the geometry of this pipe is the same like the Epley per-heliometers. So the diaphragms and diameter and the length of the pipe. So the geometry is absolutely the same like the Epley per-heliometers. And by using this device, we can measure not the global, but also the direct spectral irradiance. Its sensitivity range is from 300 to 1,100 nanometer, and the spectral resolution is 1 nanometer, and the wavelength used to estimate AOD is that wavelength is well known for all of you. Okay, and generally the studies for the several studies we use the 400 nanometers because generally the 400 nanometers is the commonly used in radiation, in simpler radiation transfer models also. The beginning for measurements was 1996. Okay, and we have a sun photometer SPO2. It is an Australian manufactured in Middleton Solar in Australia. We have two in Budapest in our main observatory of the Hungarian Meteorological Service, and another in Kékes peak, that is the highest peak of Hungary. And the wavelengths, LICOR is a monochromator instrument this sun photometer is a filter instrument. And the instrument left, I think you know well. And on the right side you can see the LICOR, but it is in a box, and that is a pipe that we designed and built to the LICOR. So practically the LICOR is in the box, so you don't see the spectrophotometer, and it is an astronomical mechanics and clock drive to track the sun. So it is the sun photometer SPO2. It is one that is the reason that it is two, that when we tested the other, so that is not in Budapest but in Kékes. So and I will show you some results only by flash and very small explanation, because we have no enough time for analysis and explain the results. It is the relationship between the gray body optical depth, that I mean the optical depth that is describe the transparency, the whole sensitive range of the per-heliometer, and the AOD for 500 nanometers. The dispersion of the dots, mainly the idea was the dispersion of the dots may be that the Aerosol optical depth is the optical depth only almost only for the aerosol, and the gray belt optical depth contains several other absorption mainly from ozone and water vapor. So the idea was that we made a parametrization with the two parameter, and when V is a linear parametrization using the ozone and the water vapor. Practically, the water vapor, we use the total precipitable water that can be calculated from the radius and measurements. And the result was good because the correlation between the two optical depths increased by 30% after this parametrization. So it means it is a useful result because for stations where there is no spectrophotometer but there is a peer heliometer, we can estimate AOD value from the gray body optical depth. We can from this equation we can estimate the AOD for 500 nanometers, but evidently we can do it simply for other wavelengths. So if somebody wants to know not the 500 nanometer, but for other, only the coefficients can be changed in the equation. It is a yearly means of gray body optical depth for Budapest for that period. It shows that the transparency of the atmosphere from 1967 were worse and worse so it decreased until the early 90s, and from the early 90s the transparency of our atmosphere, the air column above Budapest increased. It is useful for studies. You know, there is nowadays very moody studies, the global dimming or brightening, and it is useful for them because most of the stations has total global radiation measurements, and to study the transparency, the long-term transparency of the atmosphere above stations, experts use total global radiation. That is good, but not so sensitive parameter to the transparency, that a parameter that directly assigned to the transmission of the atmosphere. So it shows considerable more significant effects than the global radiation. It is aerosol optical depth and gray body optical depth also for that period, and shows very similar behavior. Also the scattering parameter that I defined you first. The shape of the curve is very similar, very similar. It means that all parameter confirms the results of each other. It is an interesting result. That means is the yearly curves of mostly absolute minimum values of the diffuse to global ratio and the calculated values for the Rayleigh atmosphere. The dots are the measured diffuse to global ratio, mostly minima of the measured diffuse to global ratio, and the calculated values are the dotted lines. And you see that in reality, sometimes, evidently very rarely, we have Rayleigh atmosphere. Very rarely, but we have Rayleigh atmosphere. It is interesting because we are in a suburban area in the edge of the agglomeration of Budapest, very close to the big industrial area, and sometimes the atmosphere can be in a level that it is approaches very largely the Rayleigh atmosphere conditions. It is the gray body optical depth, yearly curves, average yearly curves of the gray body optical depth. So we have clearer atmosphere in winter and not so clear atmosphere in summer also. it is for the same for the Aerosol optical depth. It is a relationship between the AOD for 500 nanometers and the alpha wavelength exponent. At first look, it is a chaotic cluster of dots, but if you see well, there is a tendency, and it is believable that it is the reality, and I don't expect better relationships between the two parameters, because if you think about it, if we have higher AOD, there is a tendency that we have lower alpha. It's okay because it is a first supposition that if we have higher aerosol load, aerosol content in the air column, it is expected that it has a probability that it contains larger particles, but it's not sure. It's possible, but not sure. So the reverse situation is also can happen many times. This confirmed the previous figure. Is this the yearly curves of the AOD for 500 nanometers and the alpha angstrom coefficient. We have an experiment that we using the King's method. Maybe some of you knows it. It's an inverse mathematical method to compute real aerosol size distributions from the spectral aerosol optical depth. And I don't tell you anything about the details because I have short time. But we got very useful and good relationship between the particle size distributions and the alpha values. For characteristic alpha values, for example, it means that are shown on the right side of the figure. We have characteristic shape for the aerosol size distributions. There is another respect, the same studies. The first are the higher alpha values, then the average alpha values, and in the lower part of the figure you see the particle size distributions for the higher, the lower alpha values, and the corresponding shapes are very regularly change with the alpha. So we have a study relationship between AOD and Hess-Brazovsky macrosynaptic codes, and we have some effect, but I think it's not so interesting. I don't want to explain the details. Sometimes we verified forecast models. You know, Aladdin and Aero model in Europe is very common to use weather forecasting, and they have solar radiation output, forecasted solar radiation parameters. Aladdin model had direct global and diffuse radiation. Aero has only forecasted global radiation, and when we verified the forecasted output of the weather forecasting models, I made some studies how the difference, the deviation of the forecasted solar radiation parameter from the measured value depends on the atmospheric transparency, and we had good correlation, and it shows well the problem of the model that wants to approach to the average. So the model cannot forecast well, cannot predict well the very clear and the very polluted atmospheres. This figure shows it, but I think no, Okay, I want to hurry because it's very late. So, and the third part of my presentation is the using of UV Aerosol Optical Depth. I use from our brewer the classical 320 nanometers. We have a Mark II brewer, brewer number 152. I use from Liquor Aerosol Optical Depth and SPO2, SPO2's 4 channels. I will show you the relationship between the AOD values, what the relationships we got between the UV values and the visible AOD values. How does UV AOD depend on visible AOD spectra? It is practically a relationship between the UV AOD and the wavelength exponent, and some very interesting case studies I will show you. Evident that it would be very interesting to compare the LICOR and SPO2 AOD, but we are in a brewer meeting, so it is not the topic of this. As I mentioned, the data set is for that period, because we use the software that calculate. It is a future that I will calculate the aerosol optical depth for the previous years when the AOD is not in the B files, but we have to calculate it backwards. Cases when solar disk was uncovered by any cloud were used only. We have a very complicated and how to say multi-level method to select the uncovered cases. It depends on the problem what we used. So we have a simpler method when we use only the relative global radiation, the ratio of the measured global radiation to the possible maximum global radiation, but it's not a calculated, not a theoretical maximum, but it is determined from our very long global radiation data set. It is a simpler. There is a bit complicated, much more sophisticated if we use some special satellite image from our. We have a satellite laboratory, satellite research laboratory in your institute, and they have a special method to select and to recognize cloud type from satellites radiation data. So we have several methods, and we use what is the better or what is enough for the given problem. And I neglect the channel 412 because it started to be failed in last year. So we have some reparation. And I show you some very interesting problems with extreme situations. Okay, only some words about the calibration. Brewer is calibrated biannually by the International Ozone Service, and the standard tech checkings are done in a brewer. I do the monthly external lamp test, and the documentation from the daily routines are followed and checked. And if some problem arises, I try to modify or correct it. Liquor is calibrated. We have a manufacturer optical calibrator unit for liquor, a lamp. So it is calibrated in every 6 months. It is the recommendation from the manufacturer. And the electronics had a problem last year, so it was repaired in the factory. SPO2 is problematic because SPO2 not an absolute device. It gives out voltages, so we have to calculate the optical depth outputs from the voltages and from Langley methods. Budapest is not so optimal for Langley methods because we are almost the sea level, well, 100 meters above sea level. Also, or we have another station in Kékes, the highest peak of Hungary, but is it only 1,000 meters above sea level? So it is also not so good. But the Langley on Kékes peaks are Langley methods. Langley doing is relatively good. In Budapest, the method is that when we have there is a quasi-automatic Langley that if we have a very clear day in Budapest, an automated Langley is performed, and the results are inserted to the calculations immediately. So maybe it is correct. It is also logistically and with respect of work organization, it is very difficult to go to Kékes Mount and do the Langley. So that is the reason that we have do some substitution measurement. So at first look, I will show you the results. At first look, and most of the cases, we have very good and very nice correlations and very nice spectra. I don't want to show you because the nice and good relationships and values are not so exciting. I think the peculiar days and peculiar cases are, I think, more excited and more interesting. And naturally, I will show you the results that I found for the relationships between the several wavelengths. For example, it is the effect of Icelandic volcano. I forget the name. It was in 2011, and its largest effect on our atmosphere was on April 10th of 2011. You see the violet, that's the AOD from the Brewer, the blue from the Lycor. There are some. I don't want to tell you I don't want to speak too much because I have a short time. So the data set is not completely overlapping because there was days when we didn't measure with Lycor, but with SPO2 it is continuous measurements also with Brewer. So there is some day when no simultaneous values from SPO2 and from Lycor, because Lycor we have to. Lycor is not totally automated like Brewer, so we have to turn on morning and turn off at afternoon. So it has some manpower for the measurements, and also we have not a intelligent tracker like for Brewer, but it has a astronomical clock drive, so it also can be turned on and turned off. So you see, and the orange or deep orange are the alpha values, and you see that alpha value, it is the time of the day. After it, unfortunately, it is minutes, and after it, the clouds appeared on the sky. So later, the studies had to stop. Alpha values were low. That means large particles, large dominant particle size in the early hours also, and after it suddenly started to be low, very low. There are negative values. That was that I tell you the day before yesterday, that it means some very great change and very large particles, but I cannot believe the absolute value of, because negative value it is not so, it has a good meaning, but shows us that there is a large and strong effect. AOD from Brewer relatively started to relatively speedy increases, and AOD from I think it is Lycor. Firstly it didn't detect the change in the particle. only particle in the size, particle size, only later. It is the Saharan dust above Hungary in the 4th of July 2011. It is the minutes of the day. Also, you see violet dots at the AOD for 320 nanometers, and the blue dots blue dots means the AOD, visible AOD from LICOR, and the yellow is the alpha. And this empty part means that that was cloudy. That period was cloudy. You see that alpha values were also low. It means large particles. And it's interesting that Brewer started to detect the large values earlier, and the LICOR practically didn't detect. We have didn't get any significant relationships between alpha and Brewer AOD, but I will show you what is my supposition, what would be the reason. Okay, I will show you the relationships between the several aerosol optical depths, and it is interesting because I expect that the relationships will be better between Brewer and LICOR, because LICOR is a monochromatic instrument and SPO2 a filter instrument, but very surprisingly, the correlation is better between Brewer and SPO2. So it is the relationship between Brewer AOD and the AOD, visible AOD from SPO2. It is a very good relationship. The average error of the estimation is 0.02. It means about less than 9%, and the standard deviation of the error of the estimation is 0.020. So it is a good correlation. It means that everybody can calculate visible or aerosol optical depth for 500 nanometers with a good reliability from the Brewer aerosol optical depth. They are the relationships between the Brewer aerosol optical depth, between the several aerosol optical depths calculated from the LICOR measurements. And you see the several wavelengths and the correlations. It's a relatively good, but if you see the 500, the results from the 500 is not good, but not so good than we received for obtained for the Brewer, between Brewer and the SPO2. And it is for the longest wavelength. It is some result of statistics. It means that it shows us that the calculation, if we want to calculate aerosol optical depth for visible wavelengths, it is relatively reliable up to the 500 nanometers bar. After it is not so reliable, the relative error of the estimation, and you see on the third column the standard deviation of the error of the estimation is much more higher. But it is expected, because if you see, it is not surprising, because the variability of the aerosol optical depth for the longest wavelength are very low. So if we have a higher variability at the shorter wavelengths, we didn't get significant variability in the longest wavelength. It is the result of the physical background, so not so surprising. Okay, and at final, I show you some interesting. I called it peculiar days. There are days that is absolutely don't fit, the dots from that day don't fit to the main cluster of the dots. It is again the relationship between the Brewer AOD and some other visible AOD, and you see this is the red, is the pointer. Okay. So you see this cluster, it is the same, only the same measurement, only the wavelengths. It has for all wavelengths, but I don't want to show you for all wavelengths. It is this day, so it is very away from the main cluster. And when I show you the results of the final results for the relationship, I neglected these dots from the study because it is evident that there is some special event. It means that we have a relatively low value from the visible AOD and high value from the Brewer AOD. When I study the other circumstances, I assume, I'm not sure now, but it seems to be that the reason is that the Brewer AOD, though the Brewer detects the higher particles in some cases or earlier than the visible wavelengths. That would be the reason. There are very few peculiar days. This study was come from about 60 days, and I have only 5 or 6 days with this peculiar behavior. Okay, it is another when of the Icelandic volcano. It is you can find these dots that is very far from the main cluster, so it is some peculiar behavior also. And okay, we can jump it. And there is another when the Saharan dust occurred in Hungary on 4th of July 2011. It is more problematic because in this case I'm not sure that I can separate the dots of this day or not, because for this is the dots from this day. So it is the cluster of the dots without this day, and then this figure includes this day. So it is not so away, not so far from the main cluster. So it is a decision that we include or not. Okay, some conclusions, and I finish. The wavelengths shorter than 610 nanometers are suitable to estimate visible AOD from Brewer AOD, but the extreme events, except the extreme events. And the estimation has considered the lower accuracy for the longer wavelengths due to they poorly represents the variation occurring in aerosol content of the air column. If you have a good Brewer, it is a bit exaggeration, but we are a Brewer community, so it is good to emphasize that if we have a good Brewer, the results show that if you have a good Brewer, it is worth to estimate 400 nanometer or shorter AODs rather than operate a sometimes problematic sun photometer or lower quality spectrophotometer. So it is an advertisement for the Brewer. And no relationship was found between the Brewer AOD and the visible wavelength exponent. Maybe a two-component regression is needed, and in the future I'll try to do it. And to make results more accurate, further occurring peculiar days are needed to understand the phenomenon that I showed you in the last figure, because 4 or 5 days is not enough to see the real effects. Thank you for your attention.